Start. sir, yes, sir.
Right side. Pulling is on the right side.
So we will split. Some will be here,
Left
some
on
will
the
be
right.
there. Right.
No, you have to put from the right.
Yeah.
And you said industry people. Ready?
Coming. Yeah.
ಡಿವೈಸ್ ಒಂದೊಂದು ಕ್ಯಾಮ್ರಾಗೂ ಬೇಕಾಯ್ತು.
The screen is also visible here.
Okay.
Also visible there. Whichever is
You can see there.
you are more comfortable. And this is established at the Interdisciplinary Center for Energy Research, which is a new center in the institute.
Okay.
Now, first I will explain a little bit what is supercritical carbon dioxide. It's actually any fluid can be in a supercritical state if the pressure and temperature are greater than the critical values. So, in the case of carbon dioxide, for instance, if we are above 31 degrees and we are above 73 atmospheric pressure, we are in the supercritical.
Okay.
So, we would operate a power cycle which is above that condition. So, now what is the special property? One is the high density and occupies small volume, and there are excellent thermal properties which actually would have an advantage over the conventional steam power plant. For instance, the steam power plants, they work on a cycle called Rankine cycle. I will explain here because the pointer will not work here, where we have a heat source. We have a heat source which can be runs the boiler. This heat source can be coal-based heat. It can be solar, could be nuclear, anything. But the basic cycle of steam as a motive fluid going around remains the same. So after heat is added, then steam expands in the turbine to produce the work. Then the steam has to be condensed back so that it is pumped back to the boiler pressure again. So this is the normal steam cycle. This has been working for more than 100 years, and power is generated on thermal power. It's working fine. Only thing is that the efficiency is limited. At the same time, it occupies a lot of space. So this new technology, which is working on another cycle called a Brayton cycle. This Brayton cycle is similar to that of an aircraft engine. Brayton is the person who invented the cycle in the thermodynamic. He's a thermodynamic specialist. Invented more than 200 years back this kind of cycle. Originally it was
He has invented the equation or whatever.
Equations
Using putting it to use.
Yes, initially it was done with air.
Okay.
Heat the air and then first compress the air, heat the air and then expand it to produce work. So aircraft engines have been using Brayton cycle since the beginning. But that is with air, and then the heat is added in the form of a combustion of the aircraft fuel in the gas turbine. So here the difference is that, and then the air is thrown away, the hot air. The difference here is we operate in a closed loop and we want to use carbon dioxide. Now, carbon dioxide has properties which are much better than air in terms of a working fluid to produce power. And when we operate that same cycle, which is basically compressor and after that heat addition and then expansion and then this is heat rejection, we operate in a closed cycle. If carbon dioxide is in the supercritical state, then the work done by the turbine is quite high. Work done required for the compressor is less.
Okay.
Because it behaves like a liquid here.
Adding both ways.
Yes, we are adding both ways. So we save power. So the net power output is more than a normal Brayton cycle, which is with air, and the net power output is also significantly more than the steam cycle, which is used in the thermal power plants.
Okay.
So, and the other advantage of this is it is not only higher efficiency but also very compact. Because of the high density of the supercritical carbon dioxide, even during the expansion stage, the kind of turbine that is required, the size difference is at least 1/10 to 1/20th we see. So for the supercritical carbon dioxide is of this compared to this. And this is done for a 10 megawatt electricity power plant. So this is the scale difference. And there are lots of challenges that are required to put this in practice. So theoretically everything is fine. So there are very few places in the world where we are now demonstrating the capability of this at the lab scale, at the pilot scale.
Okay.
So ours is also one of the first. Sandia National Lab was the first to establish, but they are still working on it. So in our case, these are the parameters we have chosen: 140 atmosphere, 550 degrees Celsius, and then there are certain features which will make it also adaptable.
So instead of 71, you are using 140 here.
Yeah, actually the 70 is a minimum.
That's the minimum.
So then we would have to compress it to about 140 and then expand it and bring it back to 70 again. So that is how the cycle will work. The main features of this is, apart from the difficulty of putting everything into place and make it work, we have also integrated with other forms of heat. One is the solar heat, which we will show you once we finish up with this part. And then also with Gale, we are using alternate heat, which is natural gas fire. So that project is still going on to integrate this with natural gas fire. Right now, the test loop, and I think I'll leave it to Pramod. Dr. Pramod, he is the person who developed all this one to explain what those are. So we can.
So we'd like to give you, so this is the demo thing there. So we'd like you to start one demo, then I can explain to you exactly what the loop is. You can just click. So if you see here, so this is just a demo mode, so there's nothing to it. So, those valves have opened, the system has gone into the cycle operation mode. So once the cycle is being operational, then what happens is, this is the compressor. Now from the compressor, as what Professor Pradipta mentioned, then the fluid actually is compressed to about 140 bar. This is nodal value about 114 bar, and then from here this expands. This goes into two stages of heating. What you see out here is the two heaters, first and second stage of heating. Yes, this is the big one, the long tubular one. So one of them is, suppose we don't have the solar heat available, then this will be the last facility. Then we would like to characterize under certain known conditions, control parameters. So that is why we resort to electrical heating right now. But in the real situation, the electrical heaters are going to be replaced by conventional heat sources, which could be either solar, or it could also be the gas turbine exhaust, or it also could be this combustion fuel or some fossil fuel sort of a thing. So after that, then after it is being heated, then it will go and expand into a turbine. This turbine is a critical component, and we are now collaborating with Triveni Turbines to basically develop this piece of machinery. They are also here. You can interact with them. Right now here we don't have a turbine here, so we basically simulate the turbine. So I can show you how a turbine looks. I'll show you the small scale turbine for this size, that's how it actually looks. And so if you see those three motors, basically they will bring down the pressure, and you will simulate the conditions that would have prevailed across the turbine, an actual turbine. Okay. After that, then this goes into a recuperator, where a lot of this heat is basically recovered, and this is used to supplement the. This is used to partially basically recover the heat, and then you have very little heat that needs to be added, so you can get very high cycle efficiency. So if you look at it, this is basically the turbine that you could get for this scale of a plant.
Oh, really?
Yes. So
This can generate about 20 kilowatt of power.
So I'll show you some of the heat exchangers as well. So there are some very new challenging technologies that we need to develop, and in that aspect, there are challenges. So some of them are not indigenously available. This is the first thing that we're trying to indigenize, and the second thing is the diffusion bonded heat exchanger, where you have different plates, they just bonded together. So yeah, so this basically is like a heat exchanger. So these are plates that are just bonded one on top of the other.
It's a micro-channel heat exchanger.
So we have two of such heat exchangers, one here and one out there. Then after that, the CO2 is actually cooled, and this cooling takes place through those manifolds. You see those green color lights that are on there. So water will actually flow through the heat exchanger, but there is no water loss. So eventually this water will be taken out, and you see the fans out there, they are actually running now, the dry cooler fans, they are low noise fans. So it will reject heat to the ambient. And that's how the cycle is actually complete.
So how many years from now you foresee it happening in the industry of the country?
So I would look at the time scale of about 5 years. There have been, worldwide, people have been working for the last 15 years, but there is yet to be a successful product that has been launched in the market. So what we look at is from this stage here, filling the gap and addressing all the technological needs, it will take another 5 years. At the end of 5 years, I think we should have.
So when did we start it, like the world is doing for 15 years, when did we start doing this?
We started about 5 years back.
So we started 10 years later, huh?
Yes,
As compared to
yes,
them.
yes.
So are they also going to wait for another 5 years, or they are in the process of delivering?
So there are a lot of technological challenges which have not yet been completely
By
resolved.
anyone?
By nobody till date. So Toshiba and GE, these are the companies abroad, they're working on realizing this technology, bringing it to commercialization. But I think there are some still issues that need to be addressed. So in India, it is Triveni is going to help us out with.
Good. You move on to the. This is also you have the provision. It's okay of heating it with solar. So we have taken a pipeline which goes to a small solar field because this is a small plant. Watch here. So there is a dish and concentrator, and there is a solar receiver. So instead of electric